Okay, so today I'll be presenting about parallel random sampling without replacement. Here's the, uh-oh. Oh dear. Here's kind of the overview for today. So I'll go over some background, and then I'll present about parallel Knuth shuffle with early termination. And then I'll show some interesting experiment results. And then we'll end with some discussions and conclusions. So to get things out of the way, so first thing is I want to talk about why this is not approximate nearest neighbor search anymore. So last term, my project was on ANNS or ANS. I tried implementing the algorithms that I mentioned, and then that worked kind of okay. But then when I started to implement the removal algorithms, the recall just went straight to 0, which is not very practical. Like it's basically, it becomes useless at that point. So Ajahn Kanat suggested that I should pivot to something else for graduation first, and then I can tackle ANS in my free time afterwards. So that's for this. Oh my God. Single page. Okay. So now next is the actual problem itself. Random sampling without replacement is a problem where you're given a data set X, and then you are to pick a subset of X that has size K, such that none of them repeat. This problem is used a lot in machine learning and data science in general, mostly for splitting, train test, and subsampling in order to improve efficiency or performance. And just a short recap on parallel algorithm stuff. We have two quantities that we're interested in. The first one is work, which is kind of like the single core running time or sequential running time of the algorithm. And then there's the span, which is the longest chain of dependency. So to kind of explain that, a short example is that if we have a parallel algorithm that computes A and B in parallel, and then you compute C afterwards, the work would be the sum of all of the operations that you need to do in total, and then the span would be the maximum of AB, which is run in parallel, and then the operations of C. And then here are a few algorithms that exist for random sampling. The first one is pick and remove, which is the naive solution. This one is pretty simple, where you repeatedly pick a random element from the data set K times, and then you add it to your subset, and then you return that subset. This algorithm has a sequential running time of order K, which is pretty good, but it's not very parallelizable because you basically have to do everything from start to end. Basically, you need to know which elements are left afterwards. The next one, which is kind of like the gold standard, the popular one is priority sampling. The way you do this is you assign a priority from 0 to 1 uniform to every single element, and then you can do quick select to pick the top K or minimum K elements using the priority for comparison. This one has a sequential running time of order n with high probability, which is 1 minus n, 1 over n to some constant. And of course, there are parallel algorithms that exist for quick select. So we also have a parallel variant, which does the same thing, but in parallel. And it has order n work and log square n span with high probability. And this one performs pretty well when K is very large. But the problem is when k is like, say, less than half square root of n or log of n, the problem becomes that you are doing way too much work because this is kind of dependent on the entire data set. So the last one is permutation sampling. I bring this up because this will kind of be the focus of this project. How permutation works is that you can, first you generate a swap target, H, such that the index, actually let me just draw it. So let's say the idea behind permutation is kind of like this. Oh my God. Thank you, Kabata. So you can start with an array that looks kind of like this, and then you switch things repeatedly, something kind of like that, but not necessarily like this. And it creates a permutation of the data set such that each of them have equal probability of appearing, and that's kind of the intuition behind we can use permutation for sampling. And so far, the existing algorithms run in order n or faster, or in parallel, it has log square n span. And when k is really large, or when it's approximately around n, it doesn't really matter. But when k becomes really small, then it does way too much work. So this project kind of focuses on tackling the second case using permutation sampling. But we have one small problem, which is that permutation is it looks very sequential, because how you do this is basically you start at the first index, you pick a random index from this part of the array, and then you switch. And then on the next iteration, you pick from this portion, and then you switch. And then it looks very sequential, but there's a paper by Shun et al. That says that you can run permutation or Knud's shuffle, basically, in parallel. Here are some of the useful results from the paper.
Can I ask a more fundamental question? How do you guarantee that it's uniform? Shuffle enough time, right?
If you shuffle the entire thing, then it is uniform.
If you shuffle it once, then you can get only certain permutation, right?
Yes.
So if you want to reach uniformity, you need to shuffle it a lot of time.
Yes.
So what Knud's shuffle guarantees is that the way they do it is they go from this end, right? This thing swaps with a random target. This thing swaps with a random target. What they can show is that at the end of the day, the permutation you got is uniformly chosen from one of the permutations out there.
Given enough permutation.
Given that you run through this until the end,
Only 10 times.
it's already in time.
So the useful result from that paper is that the swap target can be converted into a dependency-directed acyclic graph resembling a random binary tree. The other one is, given that we have constant time readiness detection, then we would have a parallel algorithm with order n work and log n span for Knud's shuffle with high probability. The definition for readiness will come later. And at the end is that parallel and sequential Knud's shuffle gives the same output. The first one is kind of the intuition behind how we can form a dependency graph. We start by kind of pointing which index the elements are going to be switched with, and then we form a graph that looks like this, and then you kind of modify and connect them together into one singular tree, and the paper proved that this tree shares the same distribution as a binary search tree. And that thing has log n height, essentially, which is the span of the algorithm. And then the next thing is for consent readiness detection. So here, step I is said to be ready if every step that points to I in the graph has been processed. So for example, step 8 is only ready once 3 and 7 has been processed. 6 is only ready when 4 and 5 has been processed, and so on. And the number of readiness checks of step I is its height in the graph. So the intuition behind this is that you can kind of check things in parallel for each level, and then you keep checking it until it's ready, and then once you process it, you never check it again. So for example, if you want to check the number of times that you check the readiness for 7 would be you process 2, and then you process 4 and 5, and then you process 6, and then you process 7. So in total, it would be its height in the tree. Yeah, so this one is basically the last slide. And the last one is that the parallel and the sequential one have the same output. An observation is that the leaf to root path is always ascending. So the leaf is always the smallest, and then as you go up, the index goes up. So this kind of implies that the order of swapping will happen in the same order as the sequential one, but the only difference is that you can kind of do things in parallel. And in terms of implementation, there is a technique or a framework designed by Blaylock et al. It is designed for parallel algorithms whose dependency graph is unique for each input under fork join. Fork join is basically when you start with one thread, and then you run 2 things in parallel, and that is the fork. And then after both threads return, and then you join the results together. And that's what fork join is. So for example, merge sort would only have one dependency graph for a single input because you always cut things in the middle. But something like quicksort, because you can pick the pivot randomly, you could have a case where the left side, you could have one dependency graph on the same input where the left side is smaller than the right side, and then you fork more on the right. And if you pick a pivot differently, then the left side could have more forks than the right side, or something like that. So deterministic reservation is designed to ensure determinism despite different CPU scheduling. And the main idea is that it splits a processing round or an iteration of a loop into 2 phases, which is reservation and committing. Reservation is to decide which steps are going to be processed, and then committing is actually carrying out those steps. And another thing is a primitive from deterministic reservation called write-min. The idea for write-min is that for a given memory location L and a new value X, what it does is it writes the smaller value of the two, of the value that is stored at L and X, and then you write it to L. A problem for this is that it could cause a race condition where you read the memory first, and then you compare it, but then after you write it, another thing that is bigger might be overwriting it. But we can mitigate this problem using atomic types, which basically says that every operation will be done sequentially. And for parallel Knuth shuffle, this is the reserve and commit functions. For reserve, what you want to do is you write min to the location, the index of yourself, and the index that you're going to swap with. And for commit, what you're checking is if the index you are at and the index that you're switching with is the same, then you perform the swap. Otherwise, you don't do anything. And here is a short visualization of how it works. So for example, during reservation phase, we can do reserve R5 and 5, and reserve R7 and 5. And basically these two at the same time. And this would result, so R5 and R7 are trying to swap with the same place. Not R5 and R7, sorry. R5 and R6 are trying to swap with 7, which is the same place. What would happen is, using deterministic reservation, it will ensure that R5 will be the one that gets swapped first, basically. So yeah, so index 5 and index 7 will be swapped during the first commit, and the next time it will swap 6 with 7. And finally, this is the algorithm for parallel permutation. It takes in an array and a swap target, which is kind of like how we generate the index of this swapping. What it does is it reserves things in parallel and then commit things in parallel, and then it kind of cleans up the remaining indices that it has to process in the next round. And in practice, instead of doing the entire array, what it does is it actually only does a prefix of it, but I don't think it really matters in the algorithm itself. And here is kind of how parallel permutation would work. So in the first round, in this case, we're only processing 3 steps at a time. So in the first round, you will try to switch the first 3 indices, but because index 3 needs to be swapped with index 1 first, so you only perform swap 1 and 3 and swap 2 and 5 on the next round, because you can see that the swap target does not point to anything in the prefix, so you can swap all of them at the same time in parallel. And same thing for this one, where 6 and 7, or these two indices or steps are pointing to the same target, so you only swap one of them, and then finally you swap with itself. And then that's kind of how deterministic reservation works. Now on to the popular question in algorithms class, which is, can we do better? So using Shun et al.'s parallel Knuth shuffle, we have order n work and order log n span, which is still proportional to n, but we want to improve on this by stopping after processing k elements. Because intuitively, after the first k elements are swapped, you don't really care about the rest, because you're not, like, swapping them doesn't really help with the output of the sampling, so we can stop after k. So the only difference here is that the indices that you want to swap only goes up to k, and the rest is pretty much the same. And here are some analytical results. So the first one is a definition for length of a dependency chain. This is basically telling or figuring out how long the chain of dependency is. So it is 0 if it is the last element or anything after it, because if we pick that location, we don't really care about processing anything after it, so we can just stop there. And any element, any index starting from here and after would have length 0, and then anything else would be 1 plus the length of the index that it tries to swap with. And for example, when k is 4, so we only go up to you only want to switch the first 4. The length of 1 is 2 because it tries to switch with this one once, and then that's done. And then the length of dependency chain that starts at index 4 is 0 because it just points to somewhere that we don't really care about. And then the first lemma is that the expected length of the dependency chain is this quantity. So by definition, if we want to find the expected dependency chain, we can take by how many choices we have, and then what the expected length of that chain would be, and then plus 1. So for example, the first swap target, you can switch it with any of the remaining indices, and then each of them have probability of being picked of 1/8, and then you can and then each of these would be its own expected length, essentially. And some algebra, but basically using some algebra, everything works out. I don't have a better explanation, but there's a proof. Yeah, but pretty much, essentially is that everything works out into this quantity in the lemma. And then the theorem is that the longest chain of dependency, which would also be the span of the algorithm, would be order log n over n minus k. And we can see that, so the intuition for this is that the longest chain will be the first element, will always be the length of the chain that starts at the first index, because you have more indexes to pick and more algebra. What you can do is you can kind of expand the expected value from the lemma, and then eventually you end up with some harmonic number, and then you can approximate it with natural logs, and then it works out to this quantity. So the implications of this theorem is that with early termination, the span is this amount, and if k is really small, then the span is constant. But if k, and even if k is roughly about n, the span is the same, is still log n, which is the same as before. And then the next one is the work, or the sum of dependency chains. So in the original paper by Shun et al., the way that they compute the work is by summing all the heights, the expected heights of every vertex in the graph. And they were able to do that because they showed that the dependency graph is a binary tree, but because the graph because we terminate early with only k in this after k steps, there is a chance that our dependency graph is not a binary tree, or basically it could be disconnected. So instead of using some recurrence for the height of the tree, we have to do this instead. We have to sum up the expected length of dependency chain of every index that we're processing instead. So the bound works out to be this amount after a lot of algebra. But the idea is pretty much the same, which is that every chain that we see will have at most the harmonic number that we saw before this. And because there are k of them, the bound works to k log n, which is the span. A small problem with this is that this is not work efficient, meaning that if k is small, the work decreases to around k. But if k is large, then the work goes to n log n instead. But I think it doesn't make the most sense, because we're terminating an algorithm early, and that algorithm has work order n. So the math is not mathing, but I couldn't quantify like how much I couldn't really quantify how much the chains kind of merge up later on, so we're going to stick with this. So we don't really know if it's better or not, and the other thing is that we don't really know the threshold of like what k less than n means, so we have to get some empirical results, but the results are really funny. So here is the experiment setup. N is fixed at 30 million integers, and the sample size k are fixed at 10%, 25%, 50%, 75%, and 90% of n. And we ran this on a single core machine, a 12-core machine, and a 12-core machine with hyperthreading, which is basically 24 threads. And here are the single core results. I'll kind of explain it to you because it might be a bit hard to read. The main result is that sequential algorithms are winning. the sequential ones are beating the parallel ones. And the parallel permutation, the parallel priority sampling implementation is winning against parallel permutation, even though it has worse span, which is really interesting. But this is only on one thread. Maybe on more threads it would change. It doesn't. So what happened was sequential permutation and sequential priority is down here. Parallel priority sampling is like second place. And then parallel permutation is slower than priority. And then if you do permutation on the full thing, then it's the slowest. And somehow if you throw more threads at it, it gets slower. I'm very interested in how this worked out. I tried to make a flame graph. It is not very readable. I tried reading it. I'm still trying to read it. So yeah, very interesting results. Yeah, so I have a few other things to say, but the very big conclusion is that parallel Rust works in magical ways. I have a few hypotheses on how this happened. One is that when you're working on single-threaded or one thread, Rust can do things pretty easily. But when you start to throw more threads at it, the safety that comes with using Rust starts to be a hindrance, and it does way too many checks around. So that's kind of where the performance went, because Rust is not really built to do like weird, like accessing the same vectors from multiple threads. And we have to do quite a lot of that using this implementation. So that's kind of why I think it is slow. I intend to look into why it's slow by first understanding the flame graph that I got from it. But that is it for my presentation. Thank you. And this is the reference.